Well, there are many ways to compute fundamental groups, right? You can establish a model P equivalence, you can use fancy Van Kampen's theorem, but today we're going to talk about computing fundamental groups using covering spaces. This will allow us to compute some fundamental groups, like that of the circle, right? So we're going to use the covering of the circle, the exponential map. So the key tool we will use is the PathLifting correspondence. Now, what's cool about the covering space is that we can lift paths. So what does that mean? So let's say we have the following covering map of space B by space E, and we fix the base point little b inside big B. Now let these EIs be the points in the fiber over B so that they map to be under this covering map. Let's say we have a favorite one. We like E0 the most, okay? Then the claim is that if we have a path in B starting from little b, then it lifts to a unique path starting from E0. In other words, there's a unique path starting from E0 in E that maps down to this path in B. So why is that? So here we want to use and recall the definition of covering space. And using that, we're going to lift this path segment by segment, tiny bit of segment at a time. The idea is, remember that for this map to be a covering map, B needs to be evenly covered by the space E, right? So in particular, this little b here has to have a neighborhood that is evenly covered by these maps. That means, what does that mean? That means that the preimage of this neighborhood is going to be a disjoint union of neighborhoods that are homeomorphic to it. Right? So if so, then I can look at a small part of this path that lie in this neighborhood, maybe this yellow small part, right? Then that has a corresponding preimage in this small disk center at E0, right? So I have lifted that. So I have lifted that small little path. But then I can continue this trick. I take a point on that small path and I make that my new center, my new B. I can take a point on this small path. Let's say you can't see me, but I'm taking a point here, and then I choose another neighborhood that is evenly covered, and I extend the path uh, in there, and I find a preimage in the here. Right, and I can keep doing that, and that would give me a preimage of the whole path. So that's a rough idea. Now, but we said this is about computing fundamental groups, right? How does this path lifting thing have anything to do with the fundamental group? Well, so let's look at how the loops in B lift up to E. Okay, so let me draw this green loop. So how would it lift? Well, it will lift to some path starting from E0, but where would that path end? Well, wherever it ends, the image of the endpoint must again be B, so it must end at another point in the fiber. So maybe say E2. So this gives us an interesting idea. So we can think of the loops there almost as point in the fiber. In other words, we have a map from the loops to the fiber. So this map would map every loop center at B to the point in the fiber that is the endpoint of the lift of that loop, right? If we fix a starting point, starting at our favorite E0. In the example that I have drawn, for example here, this loop maps to the point E2. Well, now here naturally you should have stopped me and asked, there's a very natural question, right? So because the elements of the fundamental group are only defined up to homotopy, so is this map well defined up to homotopy? Well, luckily the answer is yes, and this comes from the following more general property. If we have two paths down here that are path homotopic, right, and share the same endpoints, then they will lift to path homotopic paths that have the same endpoints. And we won't go through the proof, but the idea is very simple. So the idea is that we can always lift the path homotopy also. So a path homotopy between the path F and G will lift to a path homotopy between its lifting. So we have now a well-defined map from the fundamental group, right, of the base to the fiber over the base point. So some of you might be excited and already guessed that, oh my god, this must be a bijection, and maybe that's how we figure out the fundamental group. Well, not quite. It will be in the case of the fundamental group of the circle, which is what we're trying to compute, but it's not going to be true in general. For example, the first question is it always going to be surjective? Can you come up with an example when it's not surjective? Well, an obvious example would be if E is not path connected, right? If there is this dude E4 lying over here alone, we can't connect any path to it. So this E4 is never going to be in the image. No path is going to lift to end at E4. And that actually turns out to be the only obstruction. The correspondence is going to be surjective if and only if E is path connected. And why is that? Okay, so let's say all of these EIs are connected to each other, right? Let's see why each of them must be in the image, must be the endpoint of some left. Well, let's look at, say, E3. Alright, so because E is path connected, I can draw a path between E3 and E0, starting at E0, ending at E3. Well, now I can just project this path down via the map P. The image of E3 is B, the image of E0 is also B, so that projects to a loop, right, at B. So then E3 is then the image of this loop under the PathLifting correspondence. So then we see that this correspondence is surjective if and only if E is path connected. Now how about injectivity? When would two loops, say F and G, maps to the same endpoint? Let's look at this F tilde and G tilde. Well, look, if that's the case, then this loop, if I go F tilde and then go inverse of G tilde, this loop is going to be a loop center at E0. And so here, the loop F and then G inverse should be the image of a loop center at E0. So we see that the endpoint of F tilde is going to be the same as that of G tilde if and only if this loop is actually the image of some loop centered based at E0, right? The image, so it lies in the image of the fundamental group of the covering space centered at E0. Well, saying the image of the fundamental group of E, that's a bit of a mouthful. So let us just call this H, okay? Let's call this H. So we see that here what we have is that F and G lift to the same endpoint if and only if F and G lie in the same right coset of H, right? In the fundamental group. So what does this mean? Well, this means that we do not have injection from the fundamental group of B, right? But we have an injection on the cosets of H inside the fundamental group of B. So in summary, we have the following theorem. We have an injection from the set of cosets of the fundamental group of E inside the fundamental group of B. That injection into the fiber over the base point, right here. That's given by sending every loop F to the endpoint of a lift of F, starting from E0. And note that in this correspondence is going to be bijective if and only if E is path connected. Alright, so how do we use this to find the fundamental group of S1? Well, for that we'll need to use a covering of S1. So we'll use the very natural covering from R, this wrap R around S1. This covering sends every point X in R2 cos 2 pi X sine 2 pi X. So for example, from 0 to 1, we wrap the interval 0, 1 around S1 once and then keep going on. So we see here if we choose the base point of S1 to be 1, 0, then its pre-images are going to be 0, 1, 2, 3, and also minus 1, 2, minus 2. So we see that the fiber over this base point is gonna just be Z, right? Alright, and so now there's a very nice things about R, which is that So what's the special thing about R topologically? Well, it's simply connected, right? So its fundamental group is trivial. So here in this correspondence, we see that this group here is trivial. So that actually we have an injection from the fundamental group of actually a bijection, because R is path connected, because it simply connects. So we have a bijection between the fundamental group of the circle with the integer. It actually turns out to be a group homomorphism, because the way that the loop composes actually correspond to integer addition. So by squishing this fundamental group inside the fiber over the base point, we have found out that the fundamental group of the circle is the integer.